G'day chemistry students, in this video we are looking at dot point 6.3.3. We are focusing on neutralization and looking at how neutralization is slightly different for strong and weak acids and bases. Let's get into it. When we're looking at neutralizing a strong acid and a strong base, the process is actually quite straightforward, and it's something that you've already seen in class. If we have a strong acid and a strong base, they simply neutralize each other, forming a salt and water. Those products should be neutral or very close to neutral, meaning that there aren't any further processes that take place. And that means that at the end, the pH is equal to 7. I will sort of make a little bit of a disclaimer about that though. If there is any excess acid or excess base after neutralizing, then the pH won't end up being 0. When we say that the pH is equal to 7 here, that's assuming that all of the acid is consuming all of the base and vice versa. As soon as you have any excess on either side, the resultant pH is going to be different. Things start to look a little bit more interesting when we move away from neutralization between a strong acid and a strong base. Here we're going to look at neutralization of a strong acid and a weak base. Our strong acid here is nitric acid. Our weak base that we're combining it with is ammonia. When those two things come together, very similarly to all other neutralization reactions, we end up forming a salt. Note that we're not forming water. There's no oxygen that's on the base in the form of carbonate, hydroxide, oxide, anything like that. So water's not going to get formed in this process at all. We just have our two ionic components. In particular, the ammonium here, NH4, is the conjugate acid of the ammonia, and it does act as an acid. So as a result, when we form ammonium, it's actually capable of interacting with the water that's present, the water acting as a base, to reform ammonia, but also hydronium ions. As a result, the pH of the solution is not actually going to be sitting at 7 exactly. Again, this is assuming that we consume all of the acid and the base and there's no excess on either side. But the end result is a salt with a pH of less than 7 because of this hydrolysis process. Again, the conjugate acid interacting with the water, which acts as a base in this circumstance, remembering that water is amphiprotic. But the acid and the base interacting together, forming hydronium ions. The formation of hydronium ions is going to drop that pH, only slightly. So what we end up with is an equivalence point where the pH is not going to be exactly on 7. On the flip side, if we do neutralization between a weak acid and a strong base in this example being the sodium hydroxide, the weak acid in this example being vinegar or ethanoic acid. In this reaction, we end up producing sodium acetate. This is an acetate ion, CH3COO. It's the conjugate base of the ethanoic acid. We also have water forming as an extra product as well. Very similarly, this conjugate base can undergo a process of hydrolysis. In this process, we end up reacting with water. In this case, we have a base reacting with water, meaning that the water is going to act as an acid, donating a proton, reforming ethanoic acid, and leaving behind hydroxide. In this case, what that's going to mean is that at our equivalence point, where all of the acid and base have reacted together, there's no excess on either side, we're going to end up with a pH that is greater than 7 because we've produced this little bit of extra hydroxide, meaning that the hydrogen and hydroxide levels are no longer balanced, no longer being at a pH of 7. This table just shows a little bit of a summary of how those reactions go. Just something to note that when we're looking at reacting a weak acid and a weak base, the resultant pH completely depends on the relative strengths of those acids and bases. Essentially, if you have a stronger acid compared to the base, the pH is going to shift onto the acidic side. If the acid and the base have roughly the same pKa, neither of them is going to shift the pH in either direction. If you have a stronger base versus an acid, you're going to end up with slightly more hydroxide at the end, meaning that the pH is going to increase slightly. Thank you very much. In the next video, we're going to start to look at titration. It's an analytical technique which we can use to determine the concentration of acids and bases. But until then, have a good one.